As we start our astronomy unit, before we can get into stars and galaxies and how everything got there, we do have to have a little bit of background understanding on both light and energy, and so that's where we are starting today. We do need to remember that the energy that travels through space is called radiation. And that radiation is the only type of energy that can travel through space because it travels in the form of waves, right? We know the sun's energy is getting to us from 90 plus million miles away. So that energy has got to travel through the emptiness of space, and it can do that through the form of waves. Convection and conduction can't get through the atmosphere or the universe because of the lack of molecules there. Now, the parts of an energy wave we do need to know, the term crest and the term trough. So here's our wave drawn on. Make sure you draw one for yourself, and we want to label a couple things. The crest is the top part of the wave. I always think about a surfer surfing on the crest of the wave, the highest point right as it breaks, where the trough down here is the bottom. And for this one, I always think about a pig. Pig eats out of a trough. That's the big giant bowl. So this bowl shape down here, or the bottom of the wave, is the trough. So this radiation energy is traveling through space in the form of waves, crest being the top of the wave, trough being the bottom of the wave. And thinking about then the wavelength, we actually can measure how big or how small one of these wavelengths is. And to do that, we measure either from crest to crest, so I can measure from this point here to that exact point on the next wave, or I can also measure trough to trough, and that's going to give me one wavelength. So go ahead and make sure you have all three of those things labeled on a wave that you drew in there. The crest is the top, bottom is the trough. Wavelength is 1 point to the exact same point on the next wave. So the easiest way to do it is crest to crest or trough to trough. Now, energies can come in several different wavelength sizes, and because of that, we have a little way to organize those energies called the electromagnetic spectrum. Here's a simplified chart of that. This, like we said, the size of the wavelength determines the type of energy that we have. And you read about this in the book assignment a little bit. Each energy source has its own wavelength. And here this one is shown in meters. So over here the radio waves have 10 to the 4th meters. That's a really large number. And a long wave, where over here they'd be really short, 10 to the minus 14, a really small wave. Now, stars specifically give off radio energies. They give off X-ray energy, and they also, of course, give off some visible light, but we can see them. But again, radiation is the only type of energy that can travel through space. Okay, now, radiation does travel through space at the speed of light, which is about 300,000 kilometers per second. Okay, just to give you a little perspective, that would mean the energy goes 7.5 times around the Earth in 1 second. So as fast as we can snap our fingers once, that energy has already gone around the Earth 7.5 times. Another thing we've got to know, a little background about, is frequency. And again, you had a little intro to this in the book assignment. But frequency is measuring the number of waves per second. So as I look at that view from the last slide with the different waves, if I count how many waves across 1 point per second, I can know the frequency of that energy. And we measure frequency in a unit called hertz. What we notice with frequency then is when I have shorter wavelengths, and there's less space in between the waves, we end up with a higher frequency, meaning more waves per second. Right? And so when we think about frequency, we think about how often something happens. If you frequent a restaurant, you go there quite a bit. So when I have waves that happen more frequently, that means that my frequency is going to increase. They're happening more often, producing more and more energy. So if I gave you a little question here, looking at two different waves, which one would you then tell me has a higher frequency? Again, frequency, thinking about happening more often, more waves per second. This one over here would have a high frequency, as the waves would happen more often than this one here. This one have a much lower frequency, and therefore it would have less energy. Now let's think about a heartbeat. If your heartbeat is going faster and faster at a high frequency, you're going to be producing more energy. Right? You've got more energy if your heart's beating fast than here. If your heart is beating slow, having a lower frequency, your heart is not beating quite as often, therefore you're going to be exerting less energy. Okay? Now, electromagnetic spectrum, we have to bring all these different things together. What's the size of the wave, the frequency, the energy, and we're going to even add one more, which is temperature. So this chart, again, shows the energy waves organized from longest to shortest. So we can see the wave on here, starting out with its long wavelengths, right, going all the way to its short wavelengths. So we want to label a couple of those things here on the diagram. This is my long wavelength end. Meaning over here, of course, this is my short waves. Again, knowing that by looking at the distance between the different waves, here I've got a much longer distance than I do here. Knowing the wavelength also gives me a clue to the frequency. If I have a long wavelength over here, that means my waves are happening less often, so I would be producing a low frequency. And the lower the frequency, the lower the energy. So all of these things are therefore connected. If I know the wavelength size, I can predict the frequency and the energies just from that size of the wave. Over here with the shorter waves, not a lot of distance between the two crests, means I'm going to have a high frequency. Waves are happening much more often, right? More waves per second. And the more that wave comes in, the more energy that it's going to bring. So this is also higher energy. With that frequency and energy, I can also add in a temperature prediction. My thermometer got cut off a little bit over here. But with a low energy, low frequency energy, I'm going to expect, guess what? To see a low temperature. Whereas over here, high energy, high frequency is going to give me a high temperature. And again, thinking about that correlation to the heart, right? The faster your heart's beating, the more energy you have, the more you exert energy, the higher your temperature is going to get, right? You're going to get toasty and sweaty from all that motion. Okay, so we know what each end of the electromagnetic spectrum means for the energy. Now we just have to add those energies in. There are 7 different energies, so we've got these lines here to fill in. And the type of energy that we want all the way over here on the left, the longest wavelength energy is going to be radio waves. Radio has the longest and lowest energy level of all the radiations. Microwaves, second on the list, followed by infrared. Make sure you spell that one right. It's got a little R tucked in there. Infrared. The middle right here is visible light. And we can see down here, visible light is shown to us in color because we can see that one with our naked eye. These other energies, radio, micro, infrared, I can't see those without some sort of tool, okay? So visible is the only one that we can see on a regular basis, and that's good because that gives us all the colors and awesome things we can look at. Following visible, we have ultraviolet, X-ray, and finally, the strongest of the energies, gamma energies. We don't typically see these on Earth, thank goodness. Our atmosphere absorbs most of them, but they do exist out there in the universe. Now, each one does have its own special use. Just to go through some of those uses real quick with the table on the back, we know radio is, of course, used for music. Right, listening to music, communication, TV, cell phones, all use radio signal. Microwave, we of course have that in our everyday lives. We use that to reheat food. The way it does that is it actually wiggles the water molecules inside your food, and the motion of those molecules is actually what heats up your Hot Pockets. Also can be used for radar purposes. Infrared, we hear that mostly when we're talking about night vision goggles. Sometimes when we watch those criminal shows, they'll pull out night vision where they can see in the dark just by looking at the heat coming from different objects, specifically people or cars. Of course, visible, like we said, we use that to see things, yay. Most of these, once you kind of think about it, you've heard of them, you've experienced them in life. Ultraviolet, we know we get a fair amount of UV rays from the sun, being so close to it. Okay, black light is also producing some ultraviolet light for us. X-rays, we know, can go through some solid objects. Mostly we use that for skin, bones, right? We can check out different medical uses for X-ray. And then gamma, being the most powerful, like we said, most of it gets absorbed, by the Earth's atmosphere. Okay, but we can use it for some medical purposes, both sterilizing and medical imaging. Okay, we can use it for cancer treatments right now, imaging different parts of the body that the X-ray is not strong enough for, and we can even use it to see through things that are not medical related, like cars, buildings, almost like a superpower X-ray type of a situation. Okay, so electromagnetic spectrum organizes all these different types of radiation that we see in the universe, from longest wave to shortest, and then knowing what we know about each wavelength or the size of its wave, we can then determine its strength, how much energy it has, the temperature that it's exuding, as well as the frequency, how often that wave occurs.